I think now the audio works. Okay, now it does. So today I will finish the acid and base titration problem. And we'll start to do a review on Unit 6 and Unit 9. So Unit 6 is thermodynamics. We study enthalpy change, and the heat transfer, and then heat equilibrium. And Unit 9, we study application of thermodynamics. So we learn what entropy is, and then how enthalpy and entropy determines the Gibbs free energy, and then how that determines the thermodynamic favorability of a process. And then for the later half of Unit 9, we learn the redox reaction, and then the electrolytic cell, galvanic cell, electrolysis, and then cell potential at equilibrium, cell potential under non-standard conditions, and then how to calculate, how to use the Faraday's law and Faraday's constant to calculate the, let's say, the number of the electrons transferred within a certain period of time, or the amount of a metal that's deposited during the electrolysis. Can you explain briefly how to identify a dipole-dipole bond? Like, when is there a dipole? So that is Unit 3, intermolecular force. So there are 3 types of intermolecular force. One is the London dispersion force, which occurs between nonpolar molecules only, and the nonpolar and the noble gas. And remember that all the molecules have London dispersion force, but nonpolar molecules have London dispersion force only. Noble gas has the London dispersion force only. And then for the dipole-dipole bond, you mean dipole-dipole attraction, right? Dipole-dipole force. We don't call it dipole-dipole bond. Like, bond is a specific term that we use for chemical bonds, which means it's some kind of attraction or interaction between 2 atoms. And when we talk about the London dispersion force, hydrogen bonding, and then dipole-dipole interaction or dipole-dipole force, those are called intermolecular force, which means they are the attraction between the molecules, not between the atoms. So we don't use the terminology bond when it comes to dipole-dipole. And then for dipole-dipole force, that's pretty easy. So any molecule, any polar molecule. So polar molecule all have the dipole-dipole force or dipole-dipole attraction. And out of these polar molecules, those extremely polar molecules, which means the molecule that has a hydrogen bonded to a oxygen or nitrogen or fluorine. So out of all of these polar molecules, some of them are a little bit more polar than the other. Hydrogen bonding to oxygen or nitrogen or fluorine. These have polar dipole-dipole force and the hydrogen bonding. Shad, did I answer your question? Okay, so let's go back to the acid-base and titration. Obviously, here's a titration curve, and it's an FRQ question. Okay, so student titrates 20 milliliters of 0.01 molar of HC7H5O3 in aqueous with 0.02 molar of sodium hydroxide using a probe to monitor the pH of the solution. The data are plotted producing the following titration curve. Using the information in the graph, estimate the pKa of this weak acid. Okay, so the analyte is the weak acid. As I said, analyte is the subject of interest. It's something that we study. So analyte is in the flask, and then the titrant, the subject, we know the concentration is in the burette. And then you are gonna gradually drop the burette into the flask and then observe if there is any color change. And then when it has reached the equivalence point, which means when the color has changed, you're gonna stop dripping the titrant in the burette, and then you measure the amount of volume added. Oh, okay. So in the AP exam, can you say that the reaction shifts to the right or left due to more moles, or do you have to compare Q and K? For for volume. What do you mean by more moles? Okay, first off, on the AP exam, it has, so the College Board AP Chemistry guideline has explicitly stated that we shouldn't use the word shift to the left or shift to the right, even though it actually does, they know what you mean, but you have to specifically use the terms of shift towards the reactants or shift toward a product. Yes, the analyte is what we're studying. That's what we're titrating. So that's the solution of the unknown concentration. So whatever the solution in the flask is the analyte. And then for equilibrium, if we want to know like in which direction it shifts, we have to compare Q and K. We can't decide it just based on a number of moles. So, okay, again, going back to acid and base, the titration. So this is a weak acid being titrated with strong base. And as I stated yesterday, the initial point where it just started, or when you haven't added any of the sodium hydroxide, any of the strong base. In this solution, we have only the weak acid. I will just represent it as HA. So we have HA only at this point. And then at the equivalence point, which means all the acid is neutralized, all the analyte is neutralized by the strong base. This is the equivalence point at this point, because all the acids react with a strong base. Now we have only the conjugate base, A minus. And half of that is in between the initial point and then the equivalence point. We have half equivalence point. So for the equivalence point, the volume of the sodium hydroxide added is 10 milliliters. 1/2 of that is 5, which means half equivalence point occurs at 5 milliliters. And at this half equivalence point, we have half of the solution is the weak acid HA, the other half is the conjugate base A minus. So the concentration of the weak acid is equal to the concentration of its conjugate base, which means at the half equivalence point, its pH value is exactly the same as pKa value, because according to Henderson-Hasselbalch equation, pH is equal to pKa plus log the concentration ratio of the conjugate base and the weak acid. And then at half equivalence point, the ratio is equal to 1. Log 1 is equal to 0. So pH is equal to pKa plus 0. So I just need to I just need to identify this half equivalence point and then estimate and try to read its pH value, which is approximately 3. I'm pretty sure you can write any value that's between 3 and like 3.2. How do I find out the value of the pKa? If you're given a titration curve, you find the half equivalence point, and then you find its corresponding pH value. That pH value is the pKa value. Next question. When the pH of the titration mixture is 4, is there a higher concentration of the weak acid or its conjugate base? Okay. Also, this is what I mentioned yesterday. So pH of 4 is somewhere between half equivalence point and then equivalence point. Remember that half equivalence point, half of the solution is acid and the other half are conjugate base. They have the same number of moles or the same concentration. At equivalence point, we have the conjugate base only. So in between these 2 points, there are more conjugate base than the acid. So pH of 4 corresponds to this point, which is in between half equivalence point and equivalence point. So of course, we have more of the conjugate base than the weak acid. And then how I explain it is pH is equal to pKa plus log concentration of the conjugate base to the concentration of the weak acid. And I can literally just plug in the pH value and then the pKa value. So 4.0 is equal to 3 plus the log of this concentration ratio. This means log of the concentration ratio is equal to 1 or anyway, that's greater than 0, which means this ratio is greater than 1. So we have more of the base than the acid. Any question regarding this acid-base titration problem? Okay, next. The student researches benzoic acid and finds that it has a similar properties to the salicylic acid. Okay, one is C7H5O2, the other one is HC7H5O3. So salicylic acid has exactly one more oxygen. Can I prove it without using the equation? Oh, can I justify it without using the equation? Oh, yes, that works. So comparing the pH and pK value. So you're just gonna just explain what I just justified using your own words without using the equation. So you're gonna state that pH of 4 is higher than pKa value of 3. And this pH value of 3 is between half equivalence point and equivalence point. So more than half of the analyte or whatever the acid that we study is already neutralized. So we have more of the conjugate base than the acid. Okay, any other question regarding F? No, okay, let's get into question number G. Okay, so we're gonna compare these two acid. The Ka for the benzoic acid is 6.3. Oh, actually, no, this is a very simple question. So the Ka for the benzoic acid is 6.3 times 10 to the power of negative 5. Calculate the pKa value. So P just refers to negative log. Remember, the pH means negative of log of the concentration of the proton. POH means negative log of the concentration of the hydroxide. So pKa literally just means taking the log of the concentration of, taking the log of the Ka value and then put a negative sign in front of that. So it is negative log 6.3 times 10 to negative 5. Which is approximately 4.2. Well, pKa always equal to pH only at the half equivalence point. Only at the half equivalence point. So, okay, take a look at this titration curve. Titration curve literally shows the change in the pH of the analyte or change in the pH of whatever the solution in the flask. And then what I mean by titration is you are gonna titrate the acid in the flask, or you're gonna neutralize the acid in the flask by adding strong base in it. So as you add a strong base, the pH of course increases. So titration curve shows that increase. It shows the change in the pH. It shows the trend. So only at the half equivalence point, pKa value is equal to the pH value. And for this question, pKa, how you calculate pKa is exactly the same as how you calculate pH or POH. Taking the log of the value and then put a negative sign. Okay, next, H, the student performs a second titration, this time titrating 20 milliliters of a 0.01 molar benzoic acid solution with 0.02 molar of sodium hydroxide. Sketch the curve that would result from this titration of benzoic acid on the following graph, which already shows the original curve. Okay, so this is the original titration curve of the salicylic acid. And then it says the initial pH of the benzoic acid is 3.11. So I just need to spot couples of the points. The initial point is 3.11, so it will be a little bit higher than the salicylic acid, approximately here, close to 3. And then the next is the half equivalence point. So half equivalence point, at half equivalence point, pH value is equal to the pKa value. And for the salicylic acid, its pKa value was approximately 3. For the benzoic acid, its pKa value is 4.2, which means at the half equivalence point, its pH value should be 4.2 as well. Okay, right here. Then I need to find at what volume half equivalence point occurs. Then I need to do some calculation. So 20 milliliters of 0.01 benzoic acid titrated with 0.02 sodium hydroxide. First off, let's try to find the equivalence point. So equivalence point occurs when all the acid is neutralized by the base. So number of moles of the acid is equal to number of moles of the base. And then concentration times volume is equal to concentration of the base times its volume. So concentration of the benzoic acid 0.01 molar multiplied by 20 milliliters is equal to concentration of the sodium hydroxide 0.02 molar multiplied by its volume, VB. So VB, which represents the volume of the sodium hydroxide added at equivalence point, is equal to 10 milliliters. So it's the same. So salicylic acid and then benzoic acid have the same equivalence point. Okay, and then which means its half equivalence point occurs at 5, 1/2 of that, 5. Which means at 5, when you have added a 5 milliliters of the sodium hydroxide, its pH value should be 4.2. So I have a second dot here. 5 milliliters and a 4.2 pH value. And then eventually, when all of the benzoic acid is titrated with a strong base, why can you use dilution to find concentration at equivalence point? Okay, good question. So again, what I mean by the equivalence point is when all the acid and base are neutralized. And in this case, analyte is the weak acid, the benzoic acid, titrant is the strong base, sodium hydroxide. And for the benzoic acid, it has 1 proton. It can donate at most 1 proton. So the mole ratio that benzoic acid and sodium hydroxide reacts is 1:1. HC3 C7H5O3. This is a benzoic acid which reacts with the sodium hydroxide, the strong base. And their acid-base reaction looks like this. The benzoic acid 1 mole of the benzoic acid reacts with 1 mole of the hydroxide, and they form 1 mole of water, and then 1 mole of benzoate, CHH5O3 minus, the conjugate base of the benzoic acid. So the mole ratio they react is 1:1, which means at equivalence point, when all of the benzoic acid is neutralized, number of moles of the benzoic acid that was in an analyte is equal to the number of moles of the base that I added. And then how do you calculate the number of moles for a solution? Number of moles for a solution is equal to its concentration times volume. So concentration of the acid multiplied by its volume, that's equal to concentration of the base multiplied by its volume. Am I going to do the entire 2022 FRQ? Well, it depends. So if I can go over every single topic today, then probably tomorrow I can go over the 2022 MCQ, because we went over more FRQ than MCQ. But I don't think I will finish the whole Unit 9 today. I can finish Unit 6 for sure, but I'm not sure if I can finish Unit 9 today. So if I can, then I will just try to go over Unit 9 tomorrow. Okay, so going back to the titration curve. Okay, so when it has reached the end, when it has passed the equivalence point, so when more of the hydroxide is added, the strong base is added. Okay, because the initial pH of the benzoic acid is higher, so eventually at this point, its pH value will also be higher. So this curve looks like this. They have an overlapping part around the near the equivalence point. And eventually it will be a little bit higher. So today is not unit 7. So unit 7 is equilibrium, and unit 8 is acid base. So this is just the leftover from yesterday. Yesterday we did acid and base. We still have some FRQ questions to go over. And once we're done with acid and base, we're going back to unit 6 and then unit 9, the thermodynamics. Okay, next, I think this is the last acid-base FRQ question for today. So we have 3 solutions, X, Y, Z. Solution X, 100 milliliters of 0.1 molar sodium hydroxide is mixed with, okay, so for each of the solution, it's mixture of the 2 different solutions. A student prepares 3 solutions X, Y, Z as described. The values of Ka for the acidic species in the solutions are given in a table below. So HBr, hydrobromic acid, has a Ka value which is much greater than 1, means it's very large. Obviously, hydrobromic acid, that's one of the strong acid. Remember, the hydrochloric acid, hydrobromic acid, and hydroiodic acids, all of these are strong acids. And the next one is HC2H3O2. I think this is acetic acid. It is a weak acid, so its Ka value is 10 to -5. Using the information above, write the letters of the solutions in the boxes below to rank the solutions in order of an increasing pH. Okay, so lowest pH means it's the most acidic one, and then the highest pH means it's the most basic one. Well, let's take a look at each of the solution. So 100 milliliters of 0.1 molar and 100 milliliters of 0.1 molar. So number of moles is the same. Again, number of moles for a solution is equal to its concentration times volume. So these 2 species have the same number of moles. And sodium hydroxide is strong base, and hydrobromic acid is strong acid. Okay, when strong base and strong acid react, they produce water. Only water forms. And the sodium cation and then bromide anion, they do not participate in a reaction. They're just spectator ions. They have nothing to do with a pH value because they do not combine. They are not bonding to the protons. They are not bonding to the hydroxide. They just do nothing. They are just separate ions and dispersed in water. So for solution X, its pH is equal to 7. It's just completely neutral. For solution Y, it's sodium bromide, which is ionic compound. And for sodium and bromide, okay, they do not react with proton. They do not react with hydroxide. So this is a completely neutral solution. With HBr, okay, when you mix something neutral and something acidic, okay, again, there will be no reaction in between these 2 solutions. And for the acid, it just dissociates into proton and then the bromide. So neutral and acid. It will have a pH value that's less than 7. It will be acidic. For solution Z, acetic acid, and then the sodium acetate. So sodium acetate is a acetate salt. That's the salt of the acetate. And then when the salts are dissolved, when salt is dissolved in water, it immediately dissociates into cations and anions. Again, sodium cations do nothing in water. In the solution, it does not affect the pH value. So what really matters to a pH value is acetic acid and its conjugate base, acetate. This is a weak acid, and then this is a weak base. Okay, so once you have the weak acid and its conjugate base in the same solution, this solution is called buffer, right? It's called a buffer solution, which can resist the pH change when strong acid or strong base is added. And how we calculate the buffer solution is by using this equation of pH is equal to pKa plus log mole ratio of the conjugate base to the concentration of the acid. Okay, and then when you mix these two, because they have the same number of moles, so their concentration in the solution is exactly the same, which makes this ratio equal to 1, which makes the log of the ratio equal to 0. That's what we call by the half equivalence point on a titration curve. So for this buffer solution, its pH is equal to the pKa value. And since it's weak acid, its pKa value will be, of course, less than 7. It will be okay, so using the Ka value for the for the acetic acid, that will be approximately 4.7. Okay, so now we need to compare the pH of solution Y and Z because they both have a pH that's less than 7. But for solution Y, that is, okay, so for solution Y, now we have a solution with a total volume of 200 milliliters. And now the concentration of the protons is equal to 1/2 of its concentration in the initial solution, so 0.05 molar. It's because you mix the 100 milliliters of the acid and then 100 milliliters of some other solution. So it's diluted, the volume has increased by 2 times. The volume has doubled, which means the concentration has halved. So its concentration is 1/2 of 0.1, which is 0.05. And then using this information, I can calculate pH, which is negative log of the concentration of the proton. So this is equal to negative of log 0.05 is equal to 1.3. So solution Y has concentration has pH of 1.3. Solution Z has constant pH of 7.4. Solution X has pH of 7. So the lowest pH value is solution Y, and then the medium one is solution Z, and then highest pH is solution X. How did I get this 4.74? Okay, so for the pKa value, you are given the Ka value, so I plug in Ka. P means negative a log. pH means negative log concentration of the proton. POH means negative of log concentration of the hydroxide ion. So pKa literally means negative of log of the Ka value. So it's negative log 1.8 times 10 to the negative 5. And that is 4.74. Why isn't hydrofluoride a strong acid? Okay, so for hydrofluoride, for any of the strong acid, how we define a strong acid is they dissociate easily. They completely dissociate when they're dissolved in aqueous solution or in water. For the hydrofluoric acid, so on the periodic table, fluorine, so fluorine is on the right top corner. So its size is very, very small. It has a very small atomic size. At the same time, it has a very, very high electronegativity, which means it attracts the electron very, very strongly when it shares the electron, when it forms the bond with another atom. So for the let's say for the hydrochloric acid, so chlorine, it has a good amount of electronegativity, but at the same time it has an appropriate size. So it can, when protons detached from it, it can it forms a chloride ion, and then it's pretty much stable. For fluorine, because of its like small size, and because of its extraordinarily high electronegativity, when it bonds to hydrogen, like this bond is just too tight. Because hydrogen is so small, so hydrogen and fluorine, they're very close to each other, which makes this bond extra strong. So proton is not easily released from hydrofluoride. Hypothetically, does the sodium and bromide ions for ion dipole attraction in the solution? Form ion dipole attraction in the solution. So in the solution, sodium cation forms ion dipole attraction with water molecule. Bromide anion also forms ion dipole attraction with water molecules. But sodium cation and bromide anion, they do not form any of the. They're surrounded by water, so they're actually isolated from each other. What are the main strong bases? Okay, good question. It's really easy to memorize. So strong base always has OH, the hydroxide involved. So any of the alkaline metal with hydroxide bonding to hydroxide, any of the alkaline earth metal bonding to hydroxide are considered strong bases. And usually in the AP exam, you will only see these 6 types of the strong bases, such as lithium hydroxide, sodium hydroxide, potassium hydroxide, and such as beryllium hydroxide, calcium hydroxide, magnesium hydroxide. Yes, any other questions? Okay, then next 2 questions. Does the pH of solution Y increase, decrease, or remain the same when 100 milliliters of water is added? And justify your answer for solution Y. So in solution Y, we have 100 milliliters of some neutral solution, another 100 milliliters of the strong acid, and then that's why the concentration of the strong acid is diluted to 1/2. Okay, so when you add an extra 100 milliliters, then the total volume of this solution increase. And while the number of moles of the protons remain the same, which means the concentration of the proton decreases, which increase the pH value. So when 100 milliliters of water is added, the total volume of the solution increases and the concentration of the proton decreases. And then a lower proton concentration means a higher pH value, less acidic or more basic. Is this acid and base? Yes, unit 8. Can you please list the acid and base that we should know? Oh, when the compound is an acid or a base. Do you mean just the acid and base, or do you mean an ionic compound and then you want to know if it's acidic or basic? If it's just acid and base, you only need to memorize the strong acid and strong base, and then if any of the acid or base are not on this list, most likely they are just weak acid and weak base. So for the strong acids, hydrochloric acid, hydrobromic acid, hydroiodic acid, and sulfuric acid, and the phosphoric acid, nitric acid, and perchloric acid. And for the strong base, anything that combines with hydroxide. So alkali metals and alkaline earth metals. And I guess what's kind of tricky is when you see an ionic compound, such as, for example, when you see an ionic compound of sodium acetate, and then let's say, oh, this solid is dissolved in water, and is the solution acidic or basic? So when an ionic compound dissolves in water, it immediately dissociates into cation and anion. So we need to take a look at both parts. And the sodium cation, that is, okay, sodium actually comes from the strong base sodium hydroxide, right? So anything that's dissociated form of the strong acid or strong base, all of those cations or anions which are dissociated from strong acid or strong base, they are just neutral. So for example, for these strong acids, when they're dissolved in water, they are going to release chloride anion, the bromide ion, and then iodide ion. All of these are considered neutral. They do not react with hydroxide. They do not react with protons. They're just neutral. They're neutral ions that do nothing, do not participate in a reaction in when it comes to acid-base reaction. So sodium, okay, and sodium is from the sodium hydroxide, the alkali metal plus hydroxide. So again, when sodium is released in water or aqueous solution, it does nothing. It has nothing to do with the acid-base reaction. This is just a neutral part. So I only need to consider this part. And this, okay, so it carries a negative sign, and then so if you add a proton on top of it, then you get CH3COOH, which is a weak acid. So when a weak acid or any acid loses a proton, then it becomes the conjugate base. So this is a weak base. So now you are actually mixing this compound, the compound of interest. It consists of two parts, the neutral part and then the weak basic part. So for this total ionic compound in a whole, it is a slightly basic compound. Or when it's dissolved in a solution, this solution is basic. Or let's say for another example, I have ammonium chloride. Again, it's dissolved in water. So again, it dissociates into ammonium cation and then the chloride anion. Okay, the chloride, it looks pretty familiar to me. Where does it come from? It comes from hydrochloric acid. So chloride ion forms when the strong acid, hydrochloric acid, completely dissociates, which means chloride has nothing to do with acid-base reaction. It's neutral part. So I only need to consider the cation part, ammonium. And ammonia comes from ammonia. So ammonia is a base. And then when ammonia gains a proton, it becomes the ammonium, which means ammonium is an acid. So this is weak base, this is weak acid. So as a whole, this ionic compound is acidic. Do we need to know how to calculate the percentage of dissociation? I don't remember seeing any of the FRQ question asking you to actually calculate it, but I feel like sometimes they ask you to compare the percentage dissociation, if the percentage dissociation like increase, decrease, or compare the percentage dissociation of two different acids or base. So percent of dissociation depends on the Ka value or Kb value. Ka or Kb, equilibrium constant, means how much an acid or a base dissociates in water. So more dissociation means the percentage ionization is of course higher. ammonium and ammonia again. So NH3 is ammonia, which is a weak base. And then ammonia is weak acid. So, like sometimes in the toilet, it doesn't smell good. That smell, the smell of the urine is actually ammonia smell. So NH4Cl, it consists of two parts, the cation part and anion part. The cation part is NH4 plus, the anion part is chloride. Let's take a look at the chloride first. Where does chloride come from? Chloride is dissociated form of the hydrochloric acid, which is a strong acid. And remember, no matter if it's strong acid or strong base, when they dissociate in water, then their cation or anion does not react. It's only the proton part or the hydroxide part that actually behave as an acid or base. The chloride part, the bromide, chloride, or sodium cation, calcium cation, magnesium cation, these cations or anions do not interact with either acid or base. So it's just neutral. While the ammonium is a weak acid. So as a whole, this is acidic. When do we use an ICE table? When there's an electrolytic equation going on, and then let's say acid and base are reacting, and then you have, let's say, 500 milliliters of whatever concentration of the acid, and then 400 milliliters of whatever the concentration of the base, and then it's asking, oh, what's the pH of the product? Then I need to use ICE table to determine what I have for the product. Do I have the acid? Are all the acids consumed? Are all the bases consumed? What do I have for the products? Do I have both acid and its conjugate base? Is it a buffer solution? That's when we need to use the ICE table, and for a lot of other equilibrium type of problems. Okay. Sorry guys, I need to cut you guys off, and then we need to go back to acid base, and then we need to start thermodynamics. So for C, the students add 0.001 mole of the sodium hydroxide to solution Y and adds 0.001 mole of sodium hydroxide to solution Z. Assume that the volume of each solution does not change when the sodium hydroxide is added. The pH, did I go over the rate law? Yes, I already went over the rate law yesterday. Yes. Yes, today we'll start thermodynamics unit 6. And then I will go over the first half of the unit 9. Assume that the volume does not change when extra sodium hydroxide is added. The pH of solution Y changes much more than pH of solution Z changes. Explain this observation. Okay, that's actually a very, very simple question. So going back to solution Y and Z, so take a look at what I put on what I wrote. So for solution Z, it's a buffer solution because it has the weak acid and then its conjugate base. So that's a buffer solution. And what is the purpose of a buffer solution? The buffer solution can resist a change in the pH when a strong base is added or when a strong acid is added, because when strong base is added, such as for this question, the hydroxide will immediately react with the weak acid. So hydroxide is immediately consumed, which means it does not affect the pH value as much as when you add the hydroxide in some other solutions, non-buffer solutions. So for C, explain this observation. You just need to mention that solution Z is a buffer solution that has both a weak acid and its conjugate base. So when hydroxide is added to solution Z, it immediately reacts with the weak acid in the buffer solution So it doesn't affect the concentration of the protons as much as solution Y. So a buffer happens when you mix a strong acid or strong base. No. Okay. So HC3H3O2, that is that's acidic acid. That's a weak acid. Buffer only occurs when you mix a weak acid, when you have weak acid and its conjugate base. And a weak acid's conjugate base is also a weak base. So it should be a pair of weak acid and base. Weak acid base conjugate pair. When you have strong acid and strong base, they immediately react. Water comes out, that's it. This is not a buffer solution. Only when you have a weak acid and its conjugate base, or a weak base and its conjugate acid. Technically, yes. So let's say for strong acids, such as hydrochloric acid, hydrobromic acid, they're conjugate base, even though we name it as base, and then we call it conjugate base, but they do not actually behave as a base. What is a base? Base should have a very high proton affinity. They like to drag, they like to capture the proton. But chloride ion, they do not capture the proton at all. So they do not actually behave or properly work as a base, even though we call that chloride and bromide as the conjugate base. And then for the weak acid, their conjugate base is actually also is not going to be strong base. So the weaker acid have a stronger conjugate base, so it's a relative, but it's not like weak acid has actually strong base as the conjugate base. When do I know it's a conjugate acid from the first place? Okay, so a pair of conjugate acid base pair so they form a pair. Okay, so when an acid loses a proton, it becomes the conjugate base. When a base captures the proton, it becomes the conjugate acid. So the difference between them is just H plus, the proton. So let's say HC2H CH3COOH. Okay, when it loses the proton, it becomes CH3COO minus. So obviously this is a pair of conjugate acid and base. They are like conjugate acid base pair because the only difference between these two species is just one single proton. So, and then let's say NH3, that is ammonia. That's the base. And then when it captures a proton, it becomes NH4 plus. For these two species, the only difference is this one has one extra proton. That's the only difference. So I know that they are conjugate acid base pair. So going back to that question, okay, so again, solution Y is just a acidic solution. It has only the strong acid in it. And solution Z is the buffer solution, and then buffer solution can resist the change in pH. When you're writing the net ionic equation for acid base or any other reaction, how do you differentiate between when water is a liquid or aqueous? Water will never be aqueous. Water is always liquid. So no matter water is in the reactant side or the product side, water is always liquid. So when I say aqueous, it means something that's dissolved in water, and water by itself is just a liquid. So proton, that's aqueous. Hydroxide, that's aqueous. But water, H2O, that's always a liquid. Oh, how does it become ions in some questions? Okay. Then, question. What do you differ? So are you talking about some questions like water behaving as an acid or water behaving as a base? So for example, HBr react with water, and then forming bromide and then hydronium. Is it the type of equation that you're referring to? Oh, only if it's aqueous, you write ions. Oh, okay. So you were thinking that because water is in the form of liquid, so it should be deleted from the net ionic equation. No, 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 no. Let me give you another example, and then you know what it means by a net ionic equation. So, for example, when you mix the silver nitrate in aqueous with, let's say, with hydrochloric acid, which is also an aqueous, AgCl, a precipitate forms. Then a precipitate is obviously insoluble in water, so it is in the solid phase. And then it will be HNO3. This is what we usually learn if you study like general chemistry or like honors chemistry, when you've not learned a net ionic equation yet. If I want to write a net ionic equation, then you are just going to separate whatever that's like dissociated in water. But it doesn't mean that you're not including the liquid or solid. So silver nitrate dissociates into silver cation and then the nitrate anion. And then for hydrochloric acid, it also dissociates into protons and the chloride anion. Okay, and then when they react, AgCl, the silver chloride, the precipitate forms, and then the other two just remains in the form of the ion. So what's actually involved in the reaction is silver cation and then the chloride anion, they combine together to form the silver chloride. So this and this and then this. So these three species, they compromise the net ionic equation. And then the solid, even though silver chloride is solid form, it's still part of the net ionic equation. Yeah, so net ionic equation doesn't mean that you have only the ions. I mean, this is not an ion. This is just neutral. It's ionic compound in the solid phase, which is not soluble. Okay, so let's go back to that question. So, okay, any question regarding this acid-base problem, regarding the buffer solution or regarding the acid strengths or regarding how to compare the pH of different solutions? How do you know which ones are aqueous? So when they're dissolved, when they're soluble in water, then they form this like aqueous state. Do you need to know acid and base to start learning thermodynamics? No, no, no. Thermodynamics has nothing to do with acid and base. This is just the leftover from yesterday. Okay, so first off, that's not a molecule. So going back to, let's say, for example, ammonium chloride, that's not a molecule. That's called ionic compound. So for the molecule cannot break up into, cannot break down into like two separate cations and anions. It never happens. They form an aqueous in water because they are ionic compounds. They're ionic solids. So caffeinol, these are not molecule. They are ionic compounds. This is also ionic compound. This is also ionic compound, but it's insoluble in water. If it's molecule, they do not dissociate. Let's say sucrose, like the table sugar, I think it's C6H12O6. And when you dissolve in water molecule, it does not dissociate. Like this is the molecule. Yes, I think in the previous video, I talked about the acid base in detail. Okay, so let's get started with the thermodynamics, which should be the theme of today. So Unit 6, thermodynamics. So first off, in thermodynamics, in this unit, primarily we deal with the energy or heat or the enthalpy. It has a lot of different names, and then some of my students are confused. They're like, oh, what do you mean by energy? What do you mean by heat? What do you mean by enthalpy? So heat is a form of energy. There are a lot of different types of energy, such as electrical energy, like kinetic energy in physics, such as gravitational potential energy, electrical potential energy, etc. Heat is just one form of energy. And then for any of the process, there will be a release of the heat, or the absorbance of the heat, or in between two objects, there is a heat transfer. So from a hotter object to a cooler object, there is always a heat flow, and then we measure this heat flow using this concept called enthalpy. So heat flow is actually something we observe in real world, and enthalpy is actually a concept that human beings we intentionally came up with. So enthalpy measures the heat flow. So in chemistry, you can just think of enthalpy as equivalent to heat energy, the amount of heat transfer. Am I going to make videos? I will make separate videos for unit 5 to 9, but I think I will post 5 and 6 today, and probably 7, 8, 9 tomorrow. So I'm not sure if everyone will have time to go through all of that. Are those called endothermic? No. So for the endothermic and exothermic, I literally just went over what it means by enthalpy, what it means by heat, what it means by energy, and then endothermic and exothermic describe a process when the when enthalpy change is like positive or negative, and then we will get there soon. So in chemistry, enthalpy, just think of it as it's almost equivalent to heat flow. The amount of heat that flows from one object to another object. And when I refer to object, it can be actually like the environment or the surroundings. So let's say a cup of hot water cools down eventually, and then what is the other object? So the other object is just consider everything surroundings, everything like in the world other than this cup of water. And then there are two types of the process, either in world. One is called endothermic, and the other one is called exothermic. And then endothermic, okay, endo means like into, exo means out of. So let's say these days I see the news every day saying that, oh, there's a huge exodus from California to other states, which means people are moving out of California. So exothermic means the energy is getting out of the system. Okay, so any of the system or any of the object, any substance, it has like internal energy, or it has like energy stored itself. And then when energy moves out, it means it's actually losing energy. So its own energy level is decreasing. So using energy diagram, how we represent it is at the very beginning, it has like pretty good amount of energy, and then gradually it loses the energy. So eventually for the product, we see a decrease in its energy level. And oh, never mind. Sorry, that's endothermic. Oh, that's exothermic. Sorry, this is exothermic because energy moves out. I was talking about exothermic reaction. Is Gibbs free energy? Yeah, Gibbs free energy is part of the thermodynamics, but that's in Unit 9. So Unit 6 is called thermodynamics. Unit 9 is called application of thermodynamics. But typically we learn the enthalpy change, entropy change, and then Gibbs free energy all together. Okay, so for the exothermic reaction, energy moves out of the substance or moves out of the system. So the system itself is gradually losing the energy. So eventually for the final product, it will have a lower energy level compared to the reactants. And then for the endothermic, it's the opposite way. So endothermic means energy moves into the system or the substance absorb energy, so its energy level gradually increases. So for the endothermic reaction, the reactants have lower energy level compared to the products. And remember that on the x-axis, it actually represents the progress of the reaction. So on the left side, that's always the reactant. On the right side, that's always the product. It's always the reactant to the product. And then we calculate the difference between these two levels. Okay, so and then how we actually calculate it is always the product minus the reactants. Either in chemistry or physics, when we say change in whatever the value, it's always the final value minus the initial value. So it's the enthalpy of the product minus the enthalpy of the reactant. So for endothermic reaction, the change in the enthalpy, we use capital letter H to represent it. The change in the enthalpy is always a positive value because that is enthalpy of enthalpy of the product minus enthalpy of the reactants. And this is a positive value. And obviously for the exothermic reaction, the difference between the products and reactants, again, that's product minus the reactants. So it's a smaller value minus a larger value. So delta H, change in the enthalpy, is always a negative value. Can the difference of heat also be calculated also by the activation energy and the activation energy of the... Yes. Yes, we will get into the activation energy soon. And when it breaks, it's endo, and when it forms exo. Yes, when the bond breaks, it takes the energy. Energy is required, energy is needed, or energy is absorbed. So that's endothermic reaction. You break the bond first, and then new bonds are formed. So when the new bonds are formed, that's exothermic reaction. It will be unit 6 and unit 9 combined, but not all the unit 9. I don't think we have time to go over all the unit 9 today. So probably we can go over the Gibbs free energy part, but not the electrochemistry part. Okay, and then how do we actually measure the enthalpy change? Because like we need to quantify, we want to know exact number. First up, we measure the enthalpy change using the calorimetry, and then we measure the temperature. That's how we measure the change in the enthalpy. So calorimetry. So that's a machine, or that's a apparatus that we use to observe the change in the temperature for a reaction or for a process. For the electrochemistry, yes, I mean the galvanic cell, electrolytic cell, the cell potential calculation, calculation of cell potential at equilibrium and under non-standard conditions, and then the Faraday's law, all of that. Those are electrochemistry. I don't think we have time for it today. Okay, so first off, for the endothermic reaction, when it absorbs the energy, it's gaining the energy from the surroundings, which means the temperature of the surrounding is decreasing. On the other hand, for the exothermic reaction, such as burning, so combustion is the most typical type of exothermic reaction. So when you're burning something, if you put your hands near it and then you can feel the heat, you can feel it's like pretty hot. It's because it's releasing energy. So its surrounding or its environment captures that energy, and then its environment has a increasing temperature. So temperature of the surroundings increase for exothermic reactions. And then for calorimeter, we measure the change in the temperature of the surrounding. So how a calorimeter look? Well, so there are multiple types of the calorimeter, and you can actually just make one by yourself. But how it looks is usually you have the insulated container. because you need to make sure that there is no heat transfer between the so-called surrounding and then the actual surrounding. You need to make sure that all the surroundings within this container captures all the energy that's released or absorbed by the reaction. And then usually we are going to put water in the container, and then we have a thermometer here. So thermometer measures the change in the temperature, and then we usually also have a stirrer. So a stirrer is just to make sure that all the water circulates and like they're mixed thoroughly, just to make sure that not like one part of the water is heated up while the other parts are like still cool. And then you will have another insulated container here, and then you will have whatever the reaction inside or some kind of process. So let's say this is a combustion reaction, then it's going to release the heat. Okay, then the amount of heat released is captured or absorbed by the water surrounding it. Then you will absorb the increase in the temperature using a thermometer, and then you can calculate it. You can calculate the amount of heat absorbed by water. And then how we calculate it is by using the formula Q is equal to mc delta T. So, okay, but how do I know that there must be a heat transfer? Because because of the thing called thermal equilibrium. So thermal equilibrium, it's just like the equilibrium between the reactants and then the products. So when we have two objects, this is object A and this is object B. If they're at the same temperature, let's say T1, then, well, actually there is heat transfer in between them. But the amount of heat transfer from B to A is the same as the amount of heat transfer from A to B. Just like in the chemical reaction equilibrium, the reverse reaction rate is the same as the forward reaction rate. So eventually A and B, they still have the same amount of energy, and then their temperature doesn't change. It's still T1 for both of them. But if their temperature is different, then there is a net heat flow from one object to the other one. So this is A, this is object C, and let's say object A is at a higher temperature, TH, and then T low. Then there will be a net heat flow from object A to B. So eventually you will observe a heat flow from A to C, and then after a period of time, they gain or they reach this thermal equilibrium. So they will reach some equilibrium temperature, but where these two objects have the same temperature. And then obviously this equilibrium temperature will be somewhere between T low and then T high. And then what we mean by that is, okay, so from T high to T equal, object A has actually lost some kind of energy. And then from T low to T equal, object C has absorbed some amount of energy. And then these two amount of energy, heat transfer is exactly the same. So Q refers to the amount of heat flow. Q of the A released is equal to Q of the C absorbed. Okay, of course, assuming that there is no heat loss to the environment, to the surroundings. So water is acting like our surrounding. Yes, in the calorimetry, water is acting as a surrounding. Of course, you can use some other material, but usually we use water. Is redox part of the electrochemistry? Yes, redox is part of Unit 9. Okay, so now we know what's equilibrium. So using the concept of equilibrium, we can use calorimetry because the amount of heat absorbed by water is equal to the amount of heat that is released by the reaction, which is the enthalpy change of the reaction. Of course, this will be a negative value, and this is a positive value, so I will have to put a negative sign. The amount of heat released by the reaction is all captured by the water. assuming that this is a perfectly insulated container, then these two values will be equal to each other. That's the only way that we can actually experimentally measure the delta H, the change in enthalpy for any of the reaction. Okay, then now we need to know how we actually calculate it. We cannot just measure it. We need to use this equation, use this formula. So mass refers to the mass of the object, which means the mass of the water surrounding it. And then C refers to the specific heat capacity. So specific capacity of every single substance differs from each other. And a specific capacity means the amount of heat required to, or the amount of energy required to raise the temperature of the substance of 1 gram of the substance by 1 Celsius degree. Okay, how did Q turn to a negative value? It's not the Q turning to a negative value. So Q is the amount of energy that's absorbed by water. So this is a positive value. Okay, so while water absorbs energy, so the amount of energy it absorbs is a positive value, delta H for this reaction, because this is an exothermic reaction, so delta H for this reaction is a negative value. So just to make sure that I match these two value, I just put a negative sign. And delta T refers to the change in temperature. And remember, it's always the final value minus the initial value. So final temperature minus initial temperature. So if there is a decrease in the temperature, then delta T is a negative value. If there is an increase in temperature, delta T is a positive value. So for example, water, which is most commonly used as the surrounding material in calorimeter. So water has a specific capacity of 4.2 joules per gram Celsius degree, which means to raise 1 gram of water, to raise its temperature by 1 Celsius degree, we need 4.2 joules of water, 4.2 joules of energy. How the heat is released if the container is insulated? No. So now we're assuming that this is the surrounding. And then the amount of heat released by the reaction is all captured by the water. I want to make sure that no other surroundings, no other actual surroundings are absorbing that amount of heat. So if all the heat released by the reaction is captured by water only, then I can just use this formula to calculate how much heat water has absorbed, aka how much of the heat is released by the reaction. Okay, great. So let's say, for example, water. Usually, like in the it will the specific capacity is given. You are not required to memorize any of that. Let's say in a calorimeter, let's say 500 grams of water. Its temperature has increased by let's say 35 Celsius degree, then what is the amount of heat that is released by this reaction? Or what is the enthalpy change of this reaction? Okay, then first off, I will have to apply this Q is equal to mc delta T equation to calculate the amount of heat absorbed by water. So Q absorbed is equal to its mass, 500 grams multiplied by 4.2 joules per grams Celsius degree times 35 degree. And then the answer is 73,500 joules. Okay, so this is the amount of heat absorbed by water, which means the enthalpy change for this reaction must be, this reaction has released the heat. So its enthalpy change is a negative value. So it's a negative Q value, which is negative 73,500 joules. I'm pretty sure you have to bring it by yourself. Does temperature have to be in K? So it doesn't really matter if the temperature is measured in Kelvin or Celsius, because the change in the temperature, that's what we care about. So 1 Kelvin change of temperature in Kelvin, let's say it's 1, then it's equal to 1 Celsius degree change. If it's Fahrenheit, then it's not the same. But for the Kelvin, because when you do the conversion between the Kelvin and Celsius degree, you merely just add up the number 273. So the difference between initial and final temperature is exactly the same value, no matter if you use the Kelvin or the Celsius degree. Okay, and now we can talk about the enthalpy change with phase change. What units? This is unit 6. And of course, if they give us a different unit like kilogram, yes, you will have to change everything based on that. Change the kilogram into grams. Or if it's given in, and then sometimes it's like a conversion between kilojoules and joules. Okay, so for the phase change, so let's say for a single substance, when it goes from solid to liquid, or from liquid to gas, it's always absorbing energy. So all of these are endothermic process. I'm not calling it endothermic reaction because phase change is not a chemical reaction. That's a physical change. So energy must be transferred from surroundings to these substances. So the solid has an increasing temperature, and then eventually it goes from solid to liquid. Think of ice. So when water is in an environment with temperature lower than 0 Celsius degree, then it forms ice. So let's say now you have an ice at -10 Celsius degree. If you want to convert it to the liquid, first off, you will have to increase the temperature to 0 Celsius degree. Okay, this process requires energy absorbance. And then again, you will have to add heat. You will need to like give it the extra energy, like provide it with heat. So eventually it will be converted into water, which is the liquid, at 0 Celsius degree. And then you add more heat, and then the water's temperature increases. The percent yield, okay. Okay, try to remind me when we're almost done with unit 6. So the other way around, when you go from gas to the liquid, then we call it condensation reaction. Sorry, just condensation, not reaction. Condensation. It released the heat. So that's actually why when you when you put your hands over like boiling water. So even if you're not touching the water itself, you are gonna feel that like your hands are kind of burned. It's because there are like water vapors, like really really hot, like gas vapors, and they're in contact with your hands, and then they release the heat to condensate to the water, to form the water on your palm, on your skin, and it releases a huge amount of energy. So that's why you're more likely to burn your hands when you touch the water vapor compared to boiling water. Okay, and next, I'm just trying to go over these enthalpy things are really really fast. So next will be the enthalpy change for a reaction, and then how we calculate the enthalpy change if we're given couples of different reactions. So what you can do is, you can apply the Hass's law, which is actually very, very simple. So this is very similar to what you do in math. Let's say for math, you have x plus y is equal to 3, 2x minus 3y is equal to 5. You have the system of the equation. Then you can actually add up the equation 1 and 2. Oh, equation 1, for example, equation 1 multiplied by 2, then it's 2x plus 2y is equal to 6. And then you can add it up with equation 2. And how you do it is you just add up the both sides. You add up the left side and you get 4x, let's say minus y is equal to, you add up the right side, 11. That's exactly the same as what we do in chemistry. So let's say for chemistry, you have couples of the reactions. For example, you have nitrogen. Okay, so for example, combustion of the carbon. Carbon reacts with oxygen gas to form carbon dioxide. This is equation 1. And for this equation, you will be given some kind of enthalpy change value, delta H1. And let's say there's a second reaction, which states that carbon reacts with 1/2 of the oxygen gas to form carbon monoxide, 1 mole of carbon monoxide. For this reaction, you are given another enthalpy change, which is delta H2. Now, what I want you to calculate is the enthalpy change for the reaction between carbon and oxygen to form carbon monoxide. So 1 mole of carbon reacts with 1/2 moles of the oxygen to form carbon monoxide. Okay, then how do you calculate the enthalpy change for this reaction using delta H1 and delta H2? Again, just like what I did for the math, you are just going to combine these two equations. So I'm going to label the first one as equation 1, the second one as equation 2. So how do I combine equation 1 and 2 to eventually get to the overall chemical equation that we want? So for the product, I have carbon monoxide. And then out of these two chemical equations, reaction 2 is the only one that has carbon monoxide involved. And they're on the same side, both on the reactant side, which means, and then they have the same coefficient of 1, which means for reaction 2, I don't have to manipulate it. I just need to place 2. Okay, and then for reaction 1, okay, what about the other one? So I have, let's say, actually, never mind. I should have used a different reaction. I should have used this one. Carbon monoxide, my bad. Carbon monoxide, one mole of carbon monoxide combines with 1/2 moles of the oxygen gas, and it produces 1 moles of the carbon dioxide gas. You need to combine these equations. Sorry, let's get started again. So you need to combine equation 1 and 2 to eventually write this overall chemical equation. And then now I'm going to try to match the reactant and the products. For the overall equation, I have 1 mole of the carbon on the reactant side. And then out of the equation 1 and 2, equation 1 is the only one that has 1 mole of carbon on the reactant side, right? For reaction 2, I don't have like pure carbon, either on the reactant side or the product side. So equation 1, I don't have to manipulate it. I just put it there. And then what about equation 2 then? So I have 1 mole of the carbon monoxide on the product side for the overall equation. And then equation 2 have 1 mole of carbon monoxide on its reactant side. So I'm going to put carbon monoxide on the reactant side. How I do it is I will have to reverse this equation 2. So equation 2 becomes carbon monoxide sorry, my bad. Can you wait for me for like 5 minutes? Like my Apple Pencil, my like Logitech crayon is running out of battery. On the other hand, but you can ask me any questions if you want. We put the carbon monoxide in the product side. Yes, we put the carbon monoxide on the product side. To do it, we need to reverse the equation 2. So it's like you are multiplying -1 on equation 2. It's like similar to that. So when you reverse it, so it becomes carbon dioxide, this decomposed into carbon monoxide and 1/2 moles of the oxygen. And then for this reverse reaction, the delta H value becomes negative delta H2. Exactly. Yes. And then you add up these two equations. So you're adding up equation 1 and reverse of equation 2. So it will be delta H1 minus delta H2. Okay, can you specify your question? Like when you say why, do you mean like which part? No, it's no need to say sorry. I'm just trying to answer your question, but I'm not quite sure what you're asking. Oh, thank you. When you reverse the equation, why do you delta? Oh, okay. So I will try to draw the energy diagram soon. So let's go back to the energy diagram. So the energy level is represented by like so the energy level of the reactants and the products. So when they are low, it means it's the low energy level. When it's high, it means high energy level, right? So what happens when you just reverse the reactant and the products? Now the difference between the product and reactant energy level is exactly the same, but now the sign has changed. So originally it was the products minus the reactants. When you reverse it, it's the reactant minus the products. So let's say for this endothermic reaction, the delta H was positive. Now when you reverse it, now it becomes negative with the same value. Oh, okay, we haven't talked about the entropy yet. So up until now, we're all talking about the enthalpy. So the amount of heat released, the amount of heat absorbed, heat transfer, all of these are related to enthalpy, not entropy. Yes, okay. And then what's the difference between enthalpy and entropy? So in chemistry, enthalpy is just approximately the same as the heat transfer, the amount of heat change. Entropy is the amount of disorderness. So let's say my room is really messy right now, then entropy for my room is pretty high. Or my room is very, very clean, everything is very ordered, then entropy is low. So in chemistry, it means how much the particles are dispersed from each other. So let's say let's say ionic solid has a very low entropy because ionic solid has the crystal lattice structure, which means cation, anion, cation, anion. They're like tightly bonded to each other. They're like highly ordered structure. Everything is so ordered, and then they don't move around like randomly. So ionic solid has a very low entropy. On the other hand, ideal gas. Ideal gas means gas particles are far from each other, and then they go through the random motion. So the particles are always going through some like the random motion in the random direction with random speed. Then the gas have very high entropy. Sometimes I do tutoring for college students when it's like physics or chemistry. But most of my students are like high school students. Some of them are middle school students, like, but they're taking like advanced courses. What is the standard enthalpy of formation? Okay, so we will talk about standard enthalpy of formation when we're done with Hess's law and the bond enthalpy. No, not chemistry. So I do teach chemistry and physics and math. For middle school, it's usually just a math. Or some of them are taking like they're doing like math competition thing. Like 6th grade or 7th grade, some of them are really good at math and they take AMC 8. So anybody like below like 8th grade can take the exam. I mean, it's basically a competition, and then yeah. But most of my students are like high school students. Heat of fusion. I'm trying to. So I know AP Physics test is on May 11th, right? So, because like AP Chem is on May the 1st. So once it's done, then I can try to upload videos for AP Physics. Are you taking AP Physics 1? Okay. So I do teach my students like AP Calculus AB or BC. But personally, I prefer like chemistry and physics over math because I feel like for calculus, a lot of times it's not explanation. It's like there are the rules and you have to follow it. We're not on the level to try to understand what's actually going on for calculus or like for math. So I feel like for calculus, it's actually a lot more practice needed than understanding, like repeated practice. Oh, AP Physics C. So to be honest, I feel like AP Physics C has not because AP Physics 1 got more difficult these years. So when I took AP Physics, that was 10 years ago, and then we didn't have AP Physics 1 back then. We have this thing called AP Physics B. That's a combination of Physics 1 and 2, but it's much, much, much easier. Like it doesn't really ask you to explain anything or like justify anything. It's very, very simple, just calculation, just plug in the numbers in the formula, that kind of it was like very easy back then. And then at a certain point, they just like separated into physics 1 and 2. But for physics C, I feel like the difficulty level is like about the same across the years. And physics C, to be honest, I think it's not super difficult, not super challenging if you know how to do the basic differentiation and integration. Oh, okay. So I've never taken AP Bio, and then I heard that AP Bio is really, really, really hard. Um, so I took AP. So when I was in high school, I took AP Chem. I took AP Physics B, which is a combination of 1 and 2. And then I took AP Physics C, Mechanics, AP Physics C, Electricity and Magnetism, and then AP Calculus BC, and then some other like non-science stuff. I feel like AP Physics C are the most challenging one, to be honest. When it comes to the difficulty, but AP Physics C has a really, really high like percentage for like scoring 5. So I don't think you can really compare the difficulty. If you can handle physics, I think taking AP Physics C is a really good way to get another AP on your transcript. And Chem, I think it's pretty difficult. I think AP Chem is pretty difficult. It has a lot of materials. Oh, really? I don't know. I'm not very good at memorization. I don't like bio much. But I heard AP Bio is very difficult. That's what I heard from all of my friends when I was at school. Okay. I'm not good at any of the social studies or like humanities, so I can't really tell about a push. I didn't even take like history class. Okay, so going back to this question, again, you are gonna reverse the second reaction. So it's like negative of the second reaction. So now reactants becomes the product becomes the reactants. 1 mole of the carbon monoxide dissociates into 1 mole of the carbon 1 mole carbon dioxide dissociate into 1 mole carbon monoxide, and 1/2 mole of the oxygen gas. So for the enthalpy, you are taking the negative of the enthalpy change for 2, and then you're adding it up with equation 1. So just carbon plus oxygen and carbon dioxide, and then it's just delta H1. So when you're adding up these to equation, then carbon dioxide get canceled out, and then 1/2 mole of the oxygen is canceled out, so you're left with only 1/2 moles of the oxygen on the reactant side. So eventually you will get this overall equation, and for this overall equation, I just add up the enthalpy change. That will be negative of delta H2 plus delta H1. Oh, really? I personally felt like acid base and then electrochemistry were the most difficult part when I was taking AP, like back then. I remember when I was taking AP, I actually didn't understand the electrochemistry part at all, but I just ended up doing a lot of FRQ questions, and then I just figured out the rule. There are some kind of rules, so I just started plugging the numbers, but I didn't really understand like what that means when I was taking AP Chem. Why did I cancel the carbon dioxide but not the oxygen? No. I did cancel out the oxygen. Okay, so for the oxygen, we have 1/2 moles of the oxygen, and on the product side, and then 1 mole of the oxygen on the reactant side. So they do get canceled out, but not on one single whole of the oxygen. Only 1/2 of that get canceled out. So you are actually left with another 1/2 of the oxygen on the reactant side. Oh, equilibrium and kinetics are also very difficult and very confusing, to be honest. I do agree. I feel like unit 5, 7, 8, 9 are all the most challenging parts. Okay, so here we have another example. So for example, let's say nitrogen monoxide reacts with oxygen, react with ozone. React with ozone, and then they forms nitrogen dioxide and then oxygen. And let's say for this reaction, the enthalpy change is delta H1. For the second reaction, it is let's say 1 mole of just oxygen atom. It forms 1/2 of the oxygen gas molecules. Let's say this is delta H2. And then the last one is 3/2 moles of the oxygen gas converts into an ozone. Let's say this is delta H3. And then you have to combine them all together to this overall chemical equation. Nitrogen monoxide reacts with 1 oxygen atom to form nitrogen dioxide. And then you will just add up the equation 1 and 2 and 3. Eventually, you will see that everything gets canceled out. So let's say ozone in reactant side and ozone on the product side, they're canceled out. And then 1/2, okay, I want 1 mole of the oxygen, another 1/2 mole of the oxygen. They add up to 3/2 moles of the oxygen on the product side. They are canceled out with, again, 1.5 moles of the oxygen on the reactant side. So eventually you have only nitrogen monoxide and oxygen atom on the reactant side, nitrogen dioxide on the product side. So again, for this reaction, how you calculate the delta H is simply just adding up the enthalpy change for each of the step or for each of the reaction. Not necessarily intermediate catalyst, so it's kind of different. So this is just we're not talking about the reaction mechanism yet. We're literally just combining couples of the reaction together. We're combining 2 separate reactions or 3 separate reactions together. And the stoichiometry and the electrolysis calculation, I think electrolysis is pretty difficult. The calculation is not difficult, but I feel like if you don't get it, it's just so confusing. Use all the reactions. Well, probably it's going to trick you and give you 3 reactions, but you actually need to use only 2. Not very likely, but there might be trick. So basically that's it. That's the Hess's law. And if you ever multiply this reaction by a constant, let's say, for example, you need to multiply by twice, everything has to be doubled, then you also multiply the enthalpy change by 2. Or let's say you need to triple it, so 3, 3, 3, 3, then you're also going to triple the enthalpy change. Or if you reverse the reaction, then you put a negative sign for the enthalpy change. And then you just try to add up all of the enthalpy change for each of the reaction. So that's Hess's law. Okay, and then now we can use Hess's law to find the enthalpy change of for a certain reaction. Okay, then first of all, we need to know the enthalpy change of the formation. So enthalpy change of formation means for any of the substance, let's say you are gonna produce, you're gonna go through some kind of process, and you're gonna form 1 mole of this substance from its pure elements, and then the change of enthalpy for this reaction is called enthalpy change of the formation. Wait, when do I multiply H? So for example, when you are given this reaction, and let's say I want you to find the enthalpy change for this reaction. Then you are going to just multiply 3 by the enthalpy change. Okay, so that's the Hass's law and the enthalpy change of formation. So a substance is formed, okay, any substance, okay, 1 mole is formed from its elements, from the elements that constitute it. Okay, and what's really important here is when I say elements, I don't mean just the atom, one single atom. The elements in the form of, in their most abundant form in nature. So for example, let's say for let's say for carbon dioxide. So I want to know the enthalpy change of the formation of carbon dioxide. Then first off, I will have to write this chemical equation. So carbon dioxide, it consists of 2 different types of the elements, carbon and oxygen. Okay, and carbon, its most abundant form is like graphite or charcoal. So carbon, 1 single atom and solid, and oxygen, it does not exist in the form of one single oxygen atom in nature. It's always in the form of O2, oxygen gas. So it's combination of the carbon in solid and oxygen gas to form carbon dioxide in gas. And then you will always have to adjust a stoichiometry. So the coefficient of the product is equal to 1. And then the enthalpy change for this reaction is called the enthalpy change of the formation of the carbon dioxide. Or let's say, for example, sucrose, the table sugar. So it has a chemical formula of C12H22O11. So it consists of 3 different types of the elements: carbon, hydrogen, and oxygen. So again, carbon is in the form of the solid. That's the most abundant form of the carbon elements. And hydrogen and oxygen, they are in the form of the gas, diatomic molecule. So it's hydrogen in gas and then oxygen in gas to form C12H22O11. Okay, and then remember that for the product side, the coefficient should always be 1. And then now I'm going to start to balance the equation. I have 22 hydrogen atoms for the product, so the coefficient of the hydrogen gas should be 11. And then for the carbon, the coefficient should be 12. For the oxygen, we have 11 oxygen atom on the product, so for the reactant, it should be 11/2 as the coefficient of the oxygen gas. Exactly. Standard enthalpy of the formation is the formation of a compound based on its natural elements. Okay, then why do we need to learn the enthalpy change of the formation? Because once you know the enthalpy change of formation of different substance, you can use Hass's law to calculate the enthalpy change for a certain reaction. Then we multiply the whole reaction by 2. Wait, why do we need to multiply the whole reaction by 2? No. We're not going to multiply by 2. Okay, so usually we will have to multiply by 2 because I don't want to see that like fraction in my balanced chemical equation. But remember that this is for enthalpy change of the formation. And then for enthalpy change of formation, I always assume that the product or the substance of interest is 1 mole. We only care about like when 1 mole of the substance is produced, what is the enthalpy change? So I want to control the coefficient of the product as 1. Usually you can have the fraction, but just for the enthalpy change of the formation. This is what we want. We want to produce only 1 mole of the product, 1 mole of the substance. And then we want to know like how much enthalpy is like, what is the enthalpy change? How much heat is absorbed or how much heat is released. So for the enthalpy change of the formation, the unit is always whatever, like kilojoules or joules per mole. So this means when you produce 1 mole of that substance, this is the amount of enthalpy change. And now we can use these 2 concepts, Hass's law and then enthalpy change of formation, to calculate the enthalpy change for any of the reaction. Okay, so let's say combustion of ethane. So C2H6 in gas reacts with oxygen, and then they form 2 moles of the carbon dioxide and 3 of the water in liquid, right? And then if I ever balance it, then it's going to be, 4 plus 3, 7. So it should be 7/2. Okay, so let's say you have now let's say you have a chemical equation that represents the combustion of the ethane. So now I'll first off, I'm gonna balance it. So when 2 moles of the ethane reacts with 7 moles of the oxygen gas, they produce 4 moles of the carbon dioxide gas and 6 moles of the water in liquid. Okay, so for this reaction, for this second reaction, I wanted to calculate the change in the enthalpy for this reaction. And now we can use the enthalpy change of the formation. So what happens here is you are gonna add up the enthalpy change of formation of the products, and then you are gonna do a subtraction. You subtract the enthalpy change of formation of the reactants. And of course, the stoichiometry matters here. So the coefficient does matter. So that's going to be 4 times enthalpy change of formation of carbon dioxide plus 6 times enthalpy change of the formation of water minus 2 times enthalpy change of formation of ethane plus 7 times enthalpy change of formation of oxygen. Okay, and what we need to pay attention here is this part is equal to 0. Okay, why is that? I know immediately that this part is equal to 0. I don't have to include it. So oxygen, if I ever write a equation that represents the formation of oxygen gas. So oxygen consists of oxygen atom only. And then oxygen, its most abundant form in nature is just oxygen gas, O2. So it's from O2 to O2. So for any of these like pure elements that are already in its most abundant form in nature, their enthalpy change of formation is 0. So let's say for hydrogen gas, nitrogen gas, oxygen gas, their enthalpy change of formation is all 0. And for all the metals, such as like copper, like zinc, like magnesium, like iron, for all of these metals, they are already in their like most abundant form in nature, which is just one single metal, like metallic atom. Their enthalpy change of formation is all 0. But for example, the enthalpy change of formation for ozone is not 0 because ozone is not the most abundant form of oxygen. So for ozone, O3. So even though it's a pure element and then it consists of only one type of the element, you will still have to write its formation equation. So it's like 3/2 moles of the oxygen gas forms 1 moles of the ozone. So for this reaction, enthalpy change of formation is not going to be equal to 0. Okay, any question regarding enthalpy change of formation and then how we use Hess's law to combine or manipulate this enthalpy change of formation to calculate the reaction enthalpy change? Oh, it's lagging so much? So to get delta H reaction, we subtract the delta H formation of products minus, yes, products minus the reactants, product minus the reactant. Okay, always remember this, find products minus reactants, but when it comes to bond enthalpy, it's the other way around. I'm going to explain it. Oh, except the last idea that, okay. So again, what is the enthalpy change of the formation of the oxygen gas? So oxygen gas is O2. So if I ever write the formation equation for O2, that's just O2 gas becomes O2 gas, which means reactants is equal to the products. So enthalpy change of formation is of course just 0. And it applies to a lot of other gases such as nitrogen gas N2, hydrogen gas H2, such as helium gas HE, like the neon gas Ne. I mean, helium, neon, noble gas, they just exist in the form of one single atom. That's the most abundant form. But for ozone, so ozone consists of oxygen atom, and then for oxygen, for this element called oxygen, its most abundant form in nature is oxygen gas, O2. So if you ever write the formation equation for ozone, then it's from oxygen gas to ozone. And the reactants and products they're not the same, which means they have different enthalpy level. So the change in the enthalpy for this reaction is obviously not 0. So for example, another example. So when two hydrogen, okay, so enthalpy change of the formation for the hydrogen atom. Okay, so it will be 1/2 of the hydrogen gas becomes one hydrogen atom in gas. Again, for this reaction, enthalpy change of formation is not equal to 0. N2, O2, I2, chlorine 2, like bromine, hydrogen, those have 0. Yeah, enthalpy change of formation. If they're reactant, yes, it doesn't matter if they're reactants or products. Delta, yeah, of course. I mean, of course, like it will be like given, or you will be given other information, and then you're asked to find only one of the unknown variable. Like you're not asked to, you don't have to memorize any of that. Okay, so that's how we use the enthalpy change of formation to find the enthalpy change of a reaction. Now let's talk about bond enthalpy. So there are two different ways to find the enthalpy change of a reaction. One is by using enthalpy change of the formation, and you always do the product minus the reactant. And the other one is bond enthalpy. And then you always do the reactant minus the product for bond enthalpy. So bond enthalpy of the reactants minus bond enthalpy of the products. So we can start with something easier. Let's say methane, combustion of methane. So it's CH4, and gas reacts with oxygen, and it produces carbon dioxide and water. Never mind, it's just 2 moles of oxygen, right? Yes. Okay, and then for this reaction, if you ever use the enthalpy change of the reaction, no, if we use enthalpy change of the formation, then it's enthalpy change of the formation of 1 carbon dioxide multiplied plus 2 times the enthalpy change of the formation of the water and minus the enthalpy change of formation of the CH4. But if we use bond enthalpy, it's the other way around. It's the reactants minus the products. And the reason is because bond enthalpy means the amount of energy needed to break a bond. So bond enthalpy is always a positive value. But remember that when the bonds are broken, it absorbs the energy. When new bonds are formed, it actually releases the energy. So for the endothermic process, which means that change in the enthalpy is positive. When bonds are formed, it's a exothermic process. Or change in the enthalpy is a negative value. So that's why when we combine them together, we are subtracting the bond enthalpy of the new formed bonds from the bond enthalpy of the broken bonds. So it's the bond enthalpy for breaking the bonds, the amount of energy needed to break the bonds, minus the amount of energy that's released from formation of the bonds. And we always break the bonds in the reactants, and then the bonds and the products are always formed. So that's why it becomes the reactants minus the products for the bond enthalpy. And for the bond enthalpy, if you want to ever use it to calculate the delta H for a reaction, then you always have to draw the Lewis-Strauss diagram. By just having a chemical formula, you can't really use bond enthalpy, because just based on a chemical formula, you can't tell like what kind of bonds there are. So let's say for CH4, I need to draw the Lewis-Strauss diagram. Then I know it consists of 4 carbon-hydrogen single bonds. And then for the oxygen, it consists of 2 oxygen-oxygen double bonds, because we have 2 of the oxygen. And then for carbon dioxide, it's 2 carbon-oxygen double bond. And then for water, that is 4 of the hydrogen-oxygen single bond. So all of these are the bonds that I need to break. I need to break 1, 2, 3, 4, 5, 6, 6 bonds in total. And then 1, 2, 3, 4, 5, 6, 6 new bonds are formed. So enthalpy change of this reaction is equal to bond enthalpy to break the carbon-hydrogen single bond. And then I have 4 carbon-hydrogen single bond. So I multiply this amount of bond enthalpy by 4. Plus I have 2 of the oxygen-oxygen double bond. So it's 2 times the bond enthalpy of oxygen-oxygen double bond. And then you subtract the bond enthalpy for the products, which are 2 times the bond enthalpy of carbon-oxygen double bond. And 4 times the bond enthalpy of the hydrogen-oxygen single bond. Yes, you have to draw them every time to be able to calculate it, unless you can just imagine it in your mind, and then you think you're pretty much confident in their Lewis structure, so you don't have to draw it. But I strongly recommend you to draw it, because like even for me, I always make mistakes. Like for the carbon oxygen, if I don't draw it, I might put just 1 times the bond enthalpy of carbon oxygen, because this is a 1 mole. And then for like, let's say for water, H2O, for one H2O molecule, you have 2 bonds, but you might put just 2 because the coefficient is 2. So I think it's always better to draw all the Lewis structure for bond enthalpy. So that's enthalpy change of a reaction, either using enthalpy change of formation or using the bond enthalpy. So that's it for enthalpy. And then now let's briefly talk about the entropy and the Gibbs free energy. So entropy is just a value that represents the disorderness. of a system. And then in chemistry, we use the arrangement of the particles in a sample to refer to the entropy. So if the particles are very ordered, let's say they are in this crystal lattice structure, then obviously they have low entropy. This is a low entropy. In a sample, if the particles are like very random, they're like everywhere, they're like far from each other, they're dispersed, then this is high entropy. Okay, and for any of the process, naturally, if you don't try to rearrange it, then entropy always increases, or entropy cannot decrease unless you put in extra energy in the system. I mean, think of it, your room, if you don't try to clean it, it will only get messier and messier. It's not gonna get cleaner, like, or more ordered. So that's just entropy. And then sometimes you will be asked to compare the entropy of a substance at different phases. So of course, solid has a high entropy compared to, solid has a low entropy compared to liquid, and liquid has low entropy compared to gas. So gas has the highest entropy, solid has the lowest entropy. Yes, I can do the percent yield. And for any of the reaction, how you calculate the entropy change is exactly the same. It's always the final minus initial. So that is the entropy of the products minus entropy of the reactants. Yeah, we're done for Unit 6. Now we're getting into Unit 9. We're going to do the first half of Unit 9, which is related to Gibbs free energy. Okay, and now there's that's it for the entropy. And now let's get into Gibbs free energy, which is the most important concept when it comes to thermodynamics. So Gibbs free energy is calculated by combining the enthalpy and entropy of a process. For any of the process or the reaction, we can combine what does the notation S mean? So S is the entropy notation. So capital letter S is the entropy notation. Kind of, but we have like the AP style questions to do. So after I'm done with all of these concepts, like we'll try to do some AP questions together. So Gibbs free energy is represented using the capital letter G. And what's really matter here is not the Gibbs free energy itself at a specific point or at a specific moment. What we care about is the change in the Gibbs free energy for a process. So Gibbs free energy process for a chemical reaction is equal to delta H, the change in the enthalpy for this reaction, minus the temperature times delta S. So we're always assuming that this reaction occurs at a constant temperature, which is not very likely, but theoretically that's how we define it. And Gibbs free energy is especially important because it tells us about the thermodynamic favorability or spontaneity. When I talk about spontaneity, it means, okay, something that happens naturally without you have to put in like a lot of energy. So let's say I'm gonna release something, I'm just gonna drop it. Okay, then I don't have to do anything. I just release my fingers and then it naturally goes from here to here, which means it dropping is a spontaneous process or a thermodynamically favorable process. So these are what we call by spontaneous reaction or thermodynamically favorable reaction. Okay, so when Gibbs free energy delta G, change in the Gibbs free energy, when it is less than 0, then this process is spontaneous, such as me dropping this card and then it just goes down. Okay, going from here to here, this dropping process is spontaneous process or thermodynamically favorable process. So these two terms are exactly the same. when delta G, the change in the Gibbs free energy, is greater than 0, then it means it's non-spontaneous process or thermodynamically unfavorable. So for example, I want to lift this calculator from the desk, then I will have to grab it and I have to put in the extra energy to actually lift it. Then this is not a spontaneous process. This is non-spontaneous or thermodynamically unfavorable process, because I am actually applying a force, or I'm actually like I'm transferring my energy to the calculator to lift it. Like the calculator is not lifted naturally just by like doing nothing. Why do we sometimes do products minus the reactants? Kavanaugh, can you elaborate on that? What do you mean by, do you mean G products minus G reactants? Or what do you mean? So for delta S, delta H, delta G, for all of them, when there's something called delta, it always means change in something, change in a value. And for delta, it's always the product minus the reactant, or final minus the initial. And that's the same across all of the science or even the math subjects. So let's say in physics, delta, let's say delta and delta E or delta PE means the final potential energy minus the initial potential energy. It's always the final value minus initial value. Remember in math, like calculus, delta X, that's always X final minus X initial. So it's not like sometimes we do products minus reactants. It's always product minus the reactants. Okay, and there are 4 different types when it comes to delta G, because you are combining delta H and delta S. And remember that for this reaction, for this formula, T is always measured in Kelvin, which means T will always be greater than 0. When T is equal to 0, we call that absolute 0, 0 Kelvin, which means at this point, at that temperature, all the particles, even the electrons, stop moving. They don't even vibrate. It's actually an impossible state. Like it's impossible to reach that phase to reach that state. Does thermodynamically favorable means more stable? Yes. Thermodynamically favorable means more stable. Yes. Okay, so because T is a positive value, so the sign of the delta G depends on the sign of these two, the delta H and delta S. So we will have four different situations. Okay, so delta H, delta S, when both of them are positive, when both of them are negative, when one of them is positive and the other one is negative. And then delta G. Okay, so again, delta G is equal to delta H minus temperature times delta S, which means if delta H is a, let's say, negative value and delta S is a positive value, remember temperature is measured in Kelvin, that's always positive. So you are subtracting a positive value from a negative value. So the answer, the difference is always a negative value. Okay, so at any temperature, so which means if both if delta H is negative and then if delta S is positive, so for this situation, it doesn't matter what the temperature is. At any temperature, delta G is always less than 0. Or the other way around. When the enthalpy change is positive and then the entropy change is negative. Remember, the temperature is measured in Kelvin, that's always positive. So you are subtracting a negative value from a positive value. Positive minus a negative value. the difference is always positive. It doesn't matter what temperature it is. So again, if the entropy is positive and enthalpy is negative, then at any temperature, delta G is greater than 0. So there is no temperature which makes this process spontaneous. And when it's positive and positive, when both of them are positive, okay, so this is a positive value, this is a positive value. If temperature is very, very high, like 1,000 Kelvin, 2,000 Kelvin, okay, then when you multiply these two, you will get a big positive value. So you are subtracting a large positive number from a small positive number, and for the difference, you will get a negative number. So when both of them are positive, then delta G is negative only at high temperature. Then what about when both of them are negative? Okay, so this is negative, this is negative. Then when temperature is pretty low, okay, so let's say temperature is low, but temperature is still positive value. So multiplying a very small positive value to a negative value, you will get a very small negative value. Okay, so when you subtract a small negative value from a bigger negative value, eventually you will get another just negative value. So at low temperature only, you will get the spontaneous or negative delta G or spontaneous reaction, given that both delta H and delta S are negative. Okay, so these are actually very, very, very important. You will always be tested about this, like at high temperature, at low temperature, in what condition you will get a spontaneous reaction, in what condition you're not gonna get, you're gonna get a non-spontaneous reaction, etc. Okay, and then for the spontaneous reaction, so now we have 3 possible spontaneous process, right? So for this one, it's just impossible to have the spontaneous reaction at all at any other temperature. Some of the spontaneous reaction is called entropy driven. Some of the others are called enthalpy driven. So what does that mean? It means sometimes the enthalpy is the factor that the primary factor that contributes to the spontaneous reaction, or the negative sign of the delta G. Yeah, so we need to memorize this table. Yes, we have to memorize a table. So let's take a look at these two. So at high temperature, okay, well, given that both of them are positive, then at high temperature, the delta G is negative. So what really contributes the negative sign of delta G? Because delta H is positive, so what actually contribute to the negative sign of delta G is this part, negative T times delta S part. So we call this one entropy-driven spontaneous reaction. So if it were not the entropy, the positive change in entropy, then enthalpy is positive, which will make the delta G positive. Okay, on the other hand, this one is called enthalpy-driven. Because when delta S is negative, then this part is positive. So what actually contribute to negative sign of delta G is negative sign of the delta H. So it's driven by the negative change in the enthalpy. And for this one, it's driven by that positive change in the entropy. And let's see, and then the thermodynamic and kinetic control and free energy and equilibrium. How long are you going live for? So I think I'm gonna for the concept, I think we're gonna stop here, and then we should start doing the AP questions. I don't know, probably it's gonna take another like 45 minutes. Okay, so all of these are from units for unit 6, and then the Gibbs free energy for unit 9. So I haven't included any of the electrochemistry question yet. Okay, so let's take a look at this MCQ question. In an experiment, 30 grams of ethane and 30 grams of propanol are placed in a separate reaction vessels. Each compound undergoes the complete combustion with excess oxygen. Which of the following best compares the quantity of heat released in each combustion reaction? Okay, so 30 grams of ethane and 30 grams of the propanol. Well, let's see. Then ethane is C2H6. So methane, ethane, propane, it needs 1 carbon, 2 carbon, 3 carbon. So ethane corresponds to 2 carbon. C2H6, when it combines with oxygen to its combustion reaction, then it's CO2, and then 3 of the H2O. Okay, I'm going to balance it out. Then for the oxygen, that is 4 plus 3, 7, so 7 over 2. Okay, so this is when 1 mole of the C2H6 react with oxygen. And for propanol, that's C3H8 plus oxygen. So that's 3 CO2 and then 4 H2O. So that's 6 plus 4, 10 oxygen. So it should be 5. Okay, and now what I'm going to do is I will have to compare the number of the moles of the ethane and propanol in 30 grams. Actually, never mind. That's propanol, not propane. My bad. So propanol, that should be C3H7 and then OH. So eventually C3H8O with oxygen, then it should be 3 CO2 and 4 H2O. And then 4 plus 6, 10. So it should be 9 over 2 oxygen here. Okay, and then for the ethane, you wanted to ask the same question? Are we supposed to know the chemical formulas of ethane and propanol? Yes, otherwise how are you going to do this question? Yes, you have to know the formula of ethane and propanol. Otherwise, you can't solve this problem. So once you know their chemical formula, now I know their molar mass. So carbon has molar mass of 12, hydrogen has molar mass of 1. So 12 times 2 plus 1 times 6, that's 24 plus 6, or 30 grams per mole, which means 30 grams of ethane is just 1 mole. For propanol, it's 3 times 12 plus 8 times 1 plus 16. So that's 36 plus 8 plus 16. That's 44 plus 16, or 60 grams per mole. So 30 grams of propanol is 0.5 moles. Okay, so when you have 1 mole of the ethane combustion and 0.5 moles of the methane combustion, which one will release more heat? Or we can try to compare the enthalpy change. Yes, those are the hydrocarbons that you should memorize. Methane, ethane, propane, butane. I don't think you need to memorize something like larger than butane. So methane, ethane, propane, butane, that's 1 carbon, 2 carbon, 3 carbon, 4 carbon. And then anything that ends with OL, O means it's alcohol, so it has that alcohol group, OH. Okay, so again, how do we do this type of question is you're gonna take a look at the number of the oxygen involved in this combustion reaction. So if you're comparing 1 mole of the ethane and then 1 mole of the propanol, then obviously propanol reacts with more oxygen. It consumes more oxygen, so it should release more heat. But we have only 0.5 moles of the propanol. which is only 1/2 of the amount of the ethane. So eventually, the amount of heat released will be greater for ethane because we have 1 mole of that, and then you have only 0.5 moles of that. And then the oxygen difference is, this is 3.5 moles, this is a 4.5 moles. The oxygen difference is not even twice. So the amount of heat released by ethane is bigger. And next, as a sample of potassium nitrate is stirred into water at 25 Celsius degree, the compound dissolves endothermically. Okay, so it absorbs energy, which means its surrounding temperature goes down. The surrounding cools down. Which of the following best explains why the process is thermodynamically favorable at 25 Celsius degree? Okay, so this is the endothermic reaction. Okay, so this is something occurs when you dissolve an ionic compound in water or in aqueous solution. So for any of the ionic compounds, such as potassium nitrate, such as table salt sodium chloride, such as potassium chloride, and etc. Okay, let me explain this question, and I will go back to the propanol question. So dissolving the ionic compounds in water, this is a spontaneous process, right? Like you don't have to put in extra energy. You just toss the compound in the water. They just naturally dissociate. Okay, then why is this thermodynamically favorable? So usually for these type of reactions or for these type of process, it actually takes energy. The enthalpy change is usually positive. The enthalpy change is usually positive, but they have a very big increase, a large increase in entropy, because let's say for potassium and then the nitrate, they were in this crystal lattice structure, but once they're dissolved in water, they immediately dissociate into separate ions. So they are very, very dispersed, and they're free to move in the solution. So they are free to move once the ionic bonds are broken. So delta S is a big amount of change. It's a big positive number for dissolution of ionic compounds. So this is a entropy-driven spontaneous reaction. So which one best explains? All endothermic processes are thermodynamically favorable? Of course not. So delta H minus temperature times delta S. If this is positive and this is negative, then you will always get a positive Gibbs free energy, no matter at what temperature. So A is not correct. B, stirring the solution during dissolution adds the energy needed to drive an endothermic process. No. So stirring is like catalyst. So stirring is like increasing the surface area. So stirring makes the reaction faster, or stirring makes the process faster, but it does not really determine if this reaction will occur or not. So let's say you're going to dissolve something that's insoluble in water. It doesn't matter how much or how vigorously you stir it. It's not going to dissolve well. So it's not B. And C, dissolving the salts decreases the enthalpy. As I said, when the crystal lattice structures are broken and then the cations and anions are released into water, then they're more dispersed in water, they're more random, they don't have that highly ordered structure, so the entropy increases. So the answer is D. Am I going live tomorrow? Yes, I am. Yes, I'm going live tomorrow. And then, okay, let's go back to the propanol question. How I calculate a number of moles. Okay, so number of moles is equal to mass divided by the molar mass, because mass is equal to number of moles multiplied by the molar mass. So we are given the mass, which is 30 grams, and propanol, once you know its chemical formula, then you can calculate its molar mass, which is 3 times molar mass of carbon-12 plus 8 times molar mass of hydrogen-1 plus 1 times molar mass of oxygen-16. So that's 36 plus 8 plus 16, which is 60 grams per mole for the propanol. So 30 grams divided by 60 grams per mole. that is 0.5 mole of the propanol. And next, okay, diamond converting to graphite. Both are pure carbon, and delta G is a negative value, which means this is a spontaneous process. Okay, which of the following best explains why the reaction represented above is not observed to occur at room temperature? This is actually a really good question that tests your knowledge on Gibbs free energy and reaction rate. So Gibbs free energy is negative. It means that this is a spontaneous reaction. It should just occur naturally, but you will never see a diamond decomposing into graphite. And that's because a spontaneous reaction doesn't mean that it's a fast reaction. Spontaneous only tells you that it's going to occur, but it might be a super slow reaction, which takes like billions of years. So A, the rate of the reaction is extremely slow because of the relatively small value of delta G for the reaction. A, that's actually the right answer. And B, entropy of the system decreased because the carbon atoms in graphite are less ordered in that of the diamond. Okay, so let's say the carbon atom in the graphite is less ordered, so disorderness increase. So entropy should actually increase when you go from diamond to graphite. It's getting less ordered. So B is not right. C, the reaction has an extremely large activation energy due to strong three-dimensional bonding among carbon atoms in diamond. D, the reaction does not occur because it is not thermodynamically favorable. Of course not. D, it is thermodynamically favorable. Oh, it's 2 a.m.? Where are you located? Are you in Hawaii? Wait, 12 hours away? So 2 a.m., that's not in... So I guess that's not China or Korea. That's not Japan. So I think I will go live either like in the morning or at noon. Because you guys have the test on May the 1st, so I don't want to do super late. Oh, okay. Probably I will do like 11 in the morning, like PST Pacific time. Oh, 12:30, like noon or like night. Probably tomorrow I will do it around like 11 a.m. Oh no, no, I don't think it's a good idea. I think you should take a good sleep right before the exam. Yeah. Okay, so the next question. So this is regarding delta G and K equilibrium constant, so we're gonna skip this for now. I will go over the rest of the unit 9 tomorrow. So for now, let's focus on the enthalpy change, the entropy change, and then the Gibbs free energy, the spontaneity. And what will we cover? I think we're going to cover the rest of the unit 9, the electrochemistry. And then we can try to go over some other topics if you have any other question. And then I think we can try to do some of the like MCQ questions and FRQ questions, just a more general review. Okay, so let's say for this one, N2O plus carbon monoxide forms nitrogen gas and carbon dioxide. The rate of the reaction represented above increased significantly in the presence of palladium. Oh, okay. This is actually about the reaction rate. This should be unit 5. Anyway, which of the following best explains this observation? Okay, so for the reaction rate, unit 7. Unit 7 is equilibrium. Yes, I already covered that. So for, okay, so when you have a catalyst speeds up the reaction, and how it does is it provides another pathway for the reaction. So usually, the palladium binds to like 2 of the reactants, so they brings the reactants together, so they can just react faster. And then by this process, it lowers the activation energy of the reaction. So if you ever draw this energy diagram, then let's say this is a, no matter if it's exothermic or endothermic, so this is the amount of activation energy for the original chemical reaction. When it lowers the activation energy, it means this part is lowered. So it's going to be A, it lowers the activation energy, so not A. And B, the palladium absorbs the heat produced in the reaction. No, it has nothing to do with the heat. It does not really absorb the heat or release the heat. One of the reactants binds on the surface of the palladium, which introduced an alternative reaction pathway with a lower activation energy. Yeah, lower activation energy. So that's the right answer. AP gives you 4 answers to pick, A, B, C, D. Which of the following is a list of the minimum amount of data needed for determining the molar enthalpy of the solution of potassium chloride in pure water? Assume that potassium chloride in aqueous has the same specific heat capacity as pure water and that the initial temperature of potassium chloride and the water are the same. I need to determine the molar enthalpy of the solution. Oh, okay. So we need to find the molar enthalpy of the solution. And A, mass of the potassium chloride, initial temperature of the water, and then the final temperature of the solution. Okay, so according to Q is equal to mc delta T. If we want to know the molar enthalpy, the catalyst lowers the activation energy. So back to this question, molar enthalpy of solution of potassium chloride. Okay, so when potassium chlorides are dissolved in water, okay, so it's gonna, it's an endothermic reaction, which means the water will cool down. The water will release the energy. Okay, then I will have to calculate the amount of heat released by water using mc times delta T. So I need to know all of these three. So it's mass of the potassium chloride, and mass of the water, yes, and then the initial temperature and the final temperature, and heat capacity of the water. Wait, is the heat capacity of the water given? Oh, so heat capacity of potassium chloride in aqueous is the same as heat capacity of water. Okay, so it should be mass of the water, initial temperature of the water, and final temperature of the water. And then for the molar enthalpy, okay, so if we want to know the molar enthalpy, just by having these three, 1, 2, 3, just by these three, I can calculate the amount of heat absorbed by water. Sorry, released by water. And then I can calculate the enthalpy change for this amount of potassium chloride solution. But if I want to know the molar enthalpy, then I need to know the number of moles of the potassium chloride. To calculate the number of moles of the potassium chloride, I need to know the mass of the potassium chloride as well. So the answer should be C. Why is it endothermic? So for any type of the dissolution of ionic compound, when they're dissolved in water, what actually happens is the ionic bonds are broken, right? If you want to break a bond, it takes their energy. So the system or the substance are absorbing the extra energy from surroundings to break the bonds. Did I answer your question? So dissolution literally means just dissolving ionic compounds in water. So they dissociate. They're soluble in water. That's it. Yeah, it's breaking the ionic bonds. So breaking the bonds always requires an energy. Yes, it's always endothermic. It doesn't matter if it's table salt or if it's like potassium chloride, potassium nitrate, ammonium chloride, everything, all the ionic compounds. And okay, so this is a typical type of the question testing on your the thermodynamic favorability. So it's a conversion between 2 moles of the nitrogen dioxide and then dinitrogen tetraoxide gas. The dimerization of nitrogen dioxide and exothermic process. So this is an exothermic process, which means delta H is negative, is represented by the equation above. The forward reaction is thermodynamically favored, which means delta G is equal to negative value. Okay, at which of the following temperature? So delta G is equal to, again, delta H minus temperature times delta S. Okay, so assuming that both of the delta G and delta H are negative, then the temperature, okay, then that this occurs when okay, so first off, so for this reaction, I need to identify if delta S is a positive or negative. So for this process, I immediately know that delta S is actually negative because for the reactants, you have 2 moles of the gas. For the products, you have only 1 mole of the gas. So I told you that gas has a very high entropy because gas particles means they are doing random motions and they're dispersed from each other. So it's decrease in the entropy. So delta S is a negative value. So this is a negative value, which means this holds true only when the temperature is low. Yes, only when the temperature is a very small positive value. So at low temperatures only. And next, this is the combustion type of reaction. But well, to be honest, it's 2:40 and I need to leave because I have classes in like 5 minutes. So tomorrow I will live stream at 11 a.m. on the Pacific time. So we have to assume that delta H is negative. We're not assuming it. It told us that it's exothermic process. So tomorrow, I think I will just continue on Unit 9. So I will go over the thermodynamic questions and then what is it? Oh, and then the rest of the Unit 9, the electrochemistry, the electrolytic cell, galvanic cell, and stuff. And then if you have any other questions, then I will try my best to answer them. The recap of all the chapters, I think it's gonna take a while to a recap for all the chapters. For tomorrow, probably 2 hour. Yes, I will post Unit 5 and Unit 6 today, but probably like really, really late because I have classes until like 8:30 p.m. today. So I think it will be like after that. Okay, so thank you guys for joining. And then I will probably see you tomorrow. Okay, bye everyone.